Welcome to another video in the series about the TI-ARM-Clang compiler. This video discusses the details of when floating point registers are preserved during interrupts. My name is George Mock, and I'm your guide. Here are some questions that are answered during this video. How do you implement an interrupt in C or C++? When the interrupt happens, what registers get preserved? And how can you tell? Now, there are several other details about interrupts that may be of interest, but I want to be clear that those details are not addressed during this video. And that includes the types of interrupts that are available on ARM systems, integrating your interrupt with a runtime operating system, an RTOS, how is the stack aligned as all this is happening, and how an interrupt return sequence is different than from a normal function. During most of this video, I will work from the command line. I realize almost none of you who view this video work from the command line yourself, and so this will be a little bit unusual. But I think by the end of the video it'll make sense as to why I did it this way. It's just a very straightforward way to show you a file, compile it, and show the results of that compilation. In this first part, we'll do a couple of prelude things. I want to show you what version of the compiler I'm using. I'm using 4.0.2.LTS. If you use a different version of the compiler, you'll see results that are very similar, very close, but not identical to what we're going to be seeing here during this video. Next thing I want to show is the contents of this directory. There are 3 source files. I will show those in turn. But I will show you right now options.txt. These are the build options that are used every time we run the compiler during the video. To review these options, -C means compile only, don't link. -G means add debug information. And the last 3 are about the details of the particular ARM CPU that is being built for. This one's a Cortex-R5, the mFloat ABI, the floating point application binary interface. Hard means there's a hardware floating point instructions and registers in the system, and this -mFPU gives the exact variant of the hardware floating point that is available. Let's look at the source code for the first example. It's intentionally very simple. All I'm doing right now is establishing a baseline for comparison for the next example. It's just a function that calls an external function. It's declared here. Very simple. Let's compile it. Then to inspect the code that was generated by the compiler, I will use this command. Let me explain this. TI-ARM objdump is a utility that's in the same bin directory as the compiler, and --source says to disassemble this object file and interlist it with statements from the source code, and we'll see that here. Anything that begins with a semicolon is a statement from the source code, and then these lines that look like this at offset 0 is the first instruction to push. Byte offset, these are byte offsets. 4 is the next, and 8 is the next, and so forth. You can see the instructions that were generated here. Now, this is the only one where I'm really going to explain instruction by instruction what's happening, because there's only 3 instructions here, and it's practical to do it. In the other examples, the sequences are longer, and it becomes impractical to explain in that degree of detail. So the first instruction, and we can see that the name of this function is example. That's how it appears in the disassembly. There's the first brace of the function. And it starts with a push instruction. It pushes R11. LR holds the return address. Now, the reason you save off LR is that the BL instruction, which is used to implement a call, means branch link. That instruction overwrites the LR register, and so it has to be saved on the stack so it can be popped off later into the PC, and that's how the return occurs. If you're just looking at this, you can be a little bit confused about, well, what function's being called. Well, that's why we use -- source. You can see the function that's being called is external function right here. Now, you probably are questioning, why is R11 being pushed here and then restored here? I mean, R11's not being used in the function. What's happening here? Well, another requirement that the compiler has to adhere to is that at the beginning of a function and at the return of a function, the stack pointer must be aligned to an 8-byte boundary. So at the beginning of this function, we can presume that the stack pointer is aligned to an 8-byte boundary. But before this call, we have to get the stack pointer to an 8-byte boundary. So the way we do that, we know we have to push one register. If you push one more, well, then you've added 8 to the stack pointer and you've maintained the alignment. Okay, so that's the only reason R11 is being used here. It's not being used to explicitly save and restore R11. Let's consider the second example. Very similar to the previous one, but the function attribute interrupt is added, and the name of the function changes to example ISR. ISR stands for interrupt service routine. Let's compile it. Notice a diagnostic comes out. The compiler issues this warning diagnostic about calling a function could clobber means overwrite, change the floating point registers that are in the system, and you should consider changing this function attribute to interrupt save FP, which is what this video is about. But just for right now, I'd like you to pretend that you don't see this big long diagnostic. You don't see it. That what you're trying to do is you just explore what does the interrupt function attribute do, and you're trying to understand it. Okay. So let's look at the code generated by the compiler for this case. And here it is. And you can see compared to the previous example, we're pushing and popping a lot more registers. Now, if you find this a little bit confusing, understand that I did this on purpose. I constructed this example that way on purpose because I know when an interrupt calls a function, the compiler is forced to save and restore all of the registers. Okay, and I want to see, well, what does that look like? What does that do? Okay, if inside the ISR you only do a few things, you don't call a function, it's only going to push and pop the registers that are modified in the function, and that's it. Let's consider the third example. So similar to the previous one, but it changes the attribute to interrupt save FP. And the name of the function is still example ISR. Let's build it. Notice no diagnostic this time. And now let's look at the code generated by the compiler. And notice how a lot more registers are getting pushed. Now it's a little bit more tricky to see that here. This first push instruction is the same. Then notice that a couple of floating point control registers are being copied into R4 and R5, and then those are pushed. And then a V push instruction is used to push all of these floating point associated registers. Okay. And then all of this is being popped off in reverse order at the end of the function. So now you can see the difference between just a regular interrupt attribute in interrupt save FP and all the extra registers that are being preserved in the interrupt save FP case. To summarize what was shown on the command line, the attribute interrupt does not preserve floating point registers. If you want to preserve the floating point registers, you have to use the attribute interrupt save FP. And when you want to see code generated by the compiler interlisted with your C source statements, use the command tirm obj dump with the option -- source and name the object file. This object file must be built with -G for this to work. I will close this video with two references. The first one is to ti.com/tirmclang. This is the home page for the tirmclang compiler. Here's where you can download it, access the documentation, and more details like that. The second reference is to e2e.ti.com. This is for customer questions on any TI product, including tirmclang. If that question is related to the compiler, it will be answered by me. Thank you for watching this video in the series about the tirmclang compiler.